So, third lecture on limits. So far, we have seen the definition of limit and the pictorial explanation of the definition of limit. Um, so, today we will start with the equivalence definition. So, the first one is sequential criteria. Now, over here, we will be looking at for different ways to check whether limit exists or not. So we have a couple of equivalent criteria for limit of a function to exist. The first one is the sequential equivalence. This is the sequential criteria for limit. So we apply some our knowledge from sequences to check whether limit of a particular function exists or not. Now, something to understand over here, why is this better to use the sequential criteria for limits? Now, in limits, our primary variable, our independent variable is x, and which is a continuous variable, right? So that sort of crawls through the real line and tries to reach to C. Now, what about the variable, independent variable in a sequence? That is n, that is a discrete variable. Now, that gallops towards infinity. That doesn't crawl to infinity, that gallops towards infinity. So that n equal to 1, 2, 3, 4, this jumps. So, a sequential and so, I mean, what is the difference? The difference is the sequence portions are countable, so they are much easier to calculate, to compute. But for a continuous variable, continuous independent variable approaching to some point, to design a numerical scheme for that will be tough compared to the sequence part. So, if we have a sequential criteria for limits, then it would be really helpful. So, what does it say? Understand very clearly. This is very important, extremely important. Let D be a non-empty subset of R, fine, and F is a function defined over D, a real valued function. Let C be a limit point. Okay, so up to here, no problem. Then for some real number L, limit extends to C, Fx is equal to L holds if and only if. Now here the criteria starts. For every sequence xn from that D minus C, we do not want C. C is a sort of band point for us. So xn is a sequence from D minus C. So from the domain without the point of limit. So for every sequence from there converging to C, xn is a sequence converging to the point C. The sequence fxn converges to L. Okay, so whenever we have a sequence converges to C, the sequence corresponding functional value sequence fxn converges to L. Then the limit at C will be L. Proof, necessary part. So we are necessary part. So let limit exist, and we are trying to prove the sequential criteria. So let limit extends to Cfx is equal to L, and xn is a sequence in D minus C, be an arbitrary sequence converging to C. Okay, so we are going to show that fxn converges to L. This is what we are going to show. Choose epsilon arbitrary. By the definition of limit for the chosen epsilon positive, we find the delta such that this thing happens. Here is the definition of limit. So for all epsilon positive, there exists delta such that for every x from the deleted delta neighborhood of C intersection D, we have the distance of fx from L is less than epsilon. So that is what I have written. For the chosen epsilon, we have chosen epsilon already. For the chosen epsilon, we find the delta such that for every point from the deleted delta neighborhood of C intersection D, the distance between distance from L of fx is less than epsilon. This is by the definition of this limit. Fine. Sorry. Now understand this. So we have found a delta already. So what we will do? We will put the xn's within the delta. This one we will put the xn's inside this. Okay, so as xn's are converging to C, we get a k natural number such that for all n greater than or equal to k, mod of xn minus C is less than delta, right? So our motive is this way. Understand this one, that for for the points in the deleted delta neighborhood of C, fx is in are inequality satisfied. So for all points in the deleted delta neighborhood of D. Now, therefore, if we can show that the points of the sequence, they go inside this deleted delta neighborhood of C after some term, after some threshold mark, then for that for those points xn, we will have fxn minus L less than epsilon. So that will give us that fxn is converging to L. So exactly that we are doing here. As xn converges to C, we get a natural number k such that for all n greater than or equal to k, mod of xn minus C is less than delta. Okay, and this is strictly less than 0 as well, because it is no point of xn is coming is equal to C. Okay, that is why this is strictly less than 0 as well. So this side, the right hand side, this inequality is coming from the definition of convergence of a sequence. So mod of xn minus C for all n greater than or equal to k, mod of xn minus C is less than delta. That is, for all n greater than or equal to k, xn belongs to the deleted delta neighborhood of C intersection D. Of course, this part is clear, because the distance of xn from C is less than delta. So that is why xn, they belong to delta neighborhood of C, and none of them is equal to C. So that is why this belongs to the deleted delta neighborhood of C intersection D as well. Therefore, by star, this is my star, this definition of limit. So therefore, what we have for all n greater than or equal to k, xn is in deleted delta neighborhood of C. So by star, for all n greater than or equal to k, xn is in deleted delta neighborhood of C. So therefore, fxn minus L is less than epsilon. So finally, we get for all n greater than or equal to k, fxn minus L is less than epsilon. For all n greater than or equal to k, this thing happens. So this means fxn, since epsilon is arbitrary, fxn converges to L. The sequence, the functional sequence converges to L. So for any sequence xn converging to C, the functional value sequence converges to L. All right. So this goes for the necessary part. Next up, we have the sufficient part. That is, provided every sequence, now every sequence is important, every sequence in every sequence converging to C, the sequence fxn converges to the same real number L, then fx equal to the limit of fx as x tends to C is L. Okay, understand this thing carefully. For every sequence xn in D minus C converging to C, of course, the sequence fxn converges to the same real number L. So, I mean, it is something to be note over here. An example is coming that if you have for one particular sequence, fxn converges to some real number. For another particular sequence, fxn is converging but converges to some another real number, then this limit thing doesn't happen. So for every sequence converging to C, the functional sequence, corresponding functional sequence converges to the same real number L. So this is the sufficient part. Let for every sequence converging to C, fxn converges to L. Then we will show that limit of fx as x tends to C is equal to L. Assume the contrary. Therefore, negating the limit of definition of limit, we get, now tell me the negation of this definition. Yeah, this is perfectly all right. I want to put a little bit more precision in the notation. Okay, there exists epsilon greater than 0, so we usually use epsilon as an arbitrary positive quantity, right? So since this is a particular epsilon we are talking about, there exists, this epsilon is not true for every other epsilon. So I would like to do it like this. There exists epsilon naught. Okay, so epsilon, this is a particular epsilon naught. This doesn't vary. This is not an arbitrary one. This is a particular one. So I write there exists an epsilon naught, such that for all delta positive, fine. Now, can you tell me what does this x depend on? It depends on delta. So x underscore delta, fine, and this underscore 0. Yeah. So this is just a filtered way, more precise way to write this thing. After negating the definition, we get for every epsilon positive such that for all delta positive there exists a point x delta from the deleted delta neighborhood of C such that the functional value at x delta violates the epsilon not distance clause. Fine. So this means, understand this thing, for every delta positive you get a violatory point. We are going to base our rest of the proof on this part. For every delta positive we get a violatory point for which the functional value at which point violates the epsilon distance clause from L. Fine. For n, every natural number n, choose delta equal to 1 over n successively. Therefore, what do we get? We choose delta is equal to 1, so we get, okay, let me write, let me say it this way, for delta equal to 1, for n equal to 1, delta equal to 1, we get a point x1 such that if x1 minus L is greater than epsilon. We take delta equal n equal to 2, delta becomes half, then we get x2 such that distance of fx2 minus L is greater than or equal to epsilon. Okay, choose for n equal to 3, so delta equal to 1/3, then you get x3, a point x3 such that x3 in the 1/3 deleted neighborhood of C such that fx2 minus L is greater than epsilon. So this way we are getting, for every natural number n we are getting like this. Therefore, for all natural number n there exists xn, there exists a point xn by this one such that there exists an xn where in the 1 by nth sorry, not nth, 1 by n radius deleted neighborhood of C, right? This is deleted delta neighborhood of C. So this is deleted 1 by n neighborhood of C. So xn is coming from 1 by n neighborhood of C such that the functional value violates the epsilon not distance clause, epsilon not proximity clause, let me say, such that mod of fxn minus L is greater than or equal to epsilon naught. Consider the sequence this xn thus generated. Consider the sequence xn, this x1, x2, x3 is this one. Of course, these xn's are coming from deleted neighborhood of C, so none of them can be C, and they are coming from intersection D as well. So this sequence is coming from D minus C. None of the points, all the points are coming from D, none of them is C. Right? So therefore, for all n, natural number n, xn belongs to this one, 1 by n deleted neighborhood of C, intersection D. This means for all n greater than, for all natural number n, mod of xn minus C is less than 1 by n. That is the definition of this neighborhood, right? This is x minus 1 by n to x plus 1 by n. That is the definition of this one. All the distances of all the points of in this neighborhood is smaller than this radius. That is the definition. So and this is deleted neighborhood, so 0 is strictly smaller than these things. So 0 strictly smaller than mod of xn minus C, which is strictly smaller than 1 by n. Now as n tends to infinity, 1 by n tends to 0. So we have 0 less than this, less than 0. So we have xn tending to C by sandwich theorem. Remember sandwich theorem from sequences? Extreme right side is converting to the same limit as of the extreme left side. So the middle one has nowhere else to go but to go there only. So mod of xn minus C is tending to 0. Hence xn is tending to C. Okay. So what do we have? Understand this thing. So we assume the contrary. So we are assume our hypothesis has been that for every sequence xn converging to C, fxn converges to L. This is our hypothesis. We want to prove that in that way we will be able to say that limit of fx is equal to L. We assume the contrary. So therefore, negating the definition, we got xn. We have found the sequence xn from the prescribed domain, that is D minus C, which is converging to C. But what happens to the functional values? The functional values, they never converge to L because fxn minus L is greater than or equal to epsilon naught. So the definition of convergence of sequence of functions is fxn minus L has to be smaller than epsilon for any choice of epsilon. So we have found a violatory epsilon so that fxn minus L does not converge to this 0. So fxn does not converge to L. So we assumed a the contrary, that is the limit does not exist there. From there we have arrived at a contradiction which contradicts our hypothesis that we have found a sequence converging to C for which the functional value sequence does not converge to L, right? Fxn minus L is greater than or equal to epsilon naught. So but for the sequence xn, double star says, what is double star? This one. Double star says that fxn minus L is greater than or equal to epsilon, so it cannot converge to L, a contradiction to our hypothesis. Hence, our assumption was not tenable. We assume the contrary. Therefore, limit of this one equal to L. Limit of fx as x tends to C is equal to L. So we will see three major applications of the sequential criteria. So the first one is checking limits. We have got two examples. The first one is examine limit x tends to 0 sine of 1 by x. This is how it looks. Okay, there is a infinite number of jumps near the point 0, and at the point 0 this is not defined. The limit does not exist there that we can suspect. We will prove that that is actually the case. The limit does not exist using this sequential criteria. Now this one you cannot possibly do using the actual definition of limit. You try to do it once and you see what kind of problems you will have. You try to apply the definition of limit on this one, checking whether this one exists or not. So I mean, you will not be able to find anything there. So we apply the sequential criteria for this one. How do we do that? Call this one as fx, fine. Then we may assume that f is defined over r minus 0. Of course, at 0, the definition, the function is not defined. So we may assume that f is defined over r minus 0. Some neighborhood of 0 will work. Choose two sequences xn and yn from r minus 0. That is my domain. So d minus c. This is my d minus c. R minus 0 where xn is equals to 1 over n pi and yn is equals to 1 over 4n plus 1 pi by 2. All right. So the idea is there are so many points which are at this one height constantly. There are so many points which are at this 0 height constantly. There are so many points which are at this -1 height constantly. There are so many points which are at half height constantly. So many points which are at -half height constantly. So many points at √3/2 height constantly. So you choose any of those sequences. You choose any two of those sequences, and one sequence will converge to say √3/2. Another one will converge to, let's say, 1. So therefore, you will have by sequential criteria, the limit will not exist. So xn, I have chosen what I have chosen. Xn is equals to 1 over n pi. 1 over n pi. That means this goes to 0. Of course, 1 over n pi goes to 0. So when I will apply sine on that, it will be sine of 1 over xn. That is 1 over n pi, that is n pi. So sine of n pi is equal to 0. So what sequence I have chosen? I have chosen this sequence, which is going to 0 from over here. So this sequence I have chosen. Fine. Other sequence what I have chosen? 1 over 4n plus 1 pi by 2. Okay. So f of yn is sine of 1 over yn. 1 over yn is 1 over 4n plus 1 pi by 2. So that is sine of 4n plus 1 pi by 2. Sine of this thing is always 1. All right. So then both xn and yn tend to 0. Yn also tends to 0. There is one n in the denominator of yn. So xn tends to 0, 1 over n pi, and yn tends to 0 as well. But for each n, if xn is sine of n pi, that is 0, and f of yn is sine of 4n plus 1 pi by 2, that is 1 always. Hence, if xn tends to 0, whereas if yn tends to 1, both are constant sequences which converge into different points. If xn converges to 0, if yn converges to 1. So by this theorem, it says that the limit cannot exist. We have two different sequences converging to the same point where we seek the limit of the function, but the functional sequences are converging to two different points. So the next example is this one, box x, the greatest integer function. From 0 to 1, it is 0. From -1 to 0, it is -1. The greatest integer smaller than or equal to x. So call f as small f, then we may assume that f is defined over all of R. Okay, so 0 is not any critical point. Choose two sequences xn and yn from r minus 0, one from the right side, one from the left side. So xn is 1 over n, yn is -1 over n. Then both x and yn tends to 0. But for each n, fxn is f of xn, that is the positive one. F of xn is the box of 1 over n, that is 0, and f of yn is box of -1 over n, that is -1. So fxn converges to 0, if yn converges to -1. That's it. So therefore, by the same theorem, limit x tends to 0, box x cannot exist.